Alrighty, welcome guys. My name is Will and this is Prash over here. So welcome to the Steels crash course. Keep it pretty informal today and just go through what you need to know before heading into the term. Kind of just break it down a little bit. So Steels crash course. So for Steels, right? For many of you, this might be your first sort of real engineering subject. So a bit of a show of hands. Has anyone done concrete structures here before? No concrete? Okay, good. You guys done mechanics of solids? Okay, cool. So I feel like this will be, well, for me at least, it was the first real subject where you really start to do a lot of engineering design. And so in that sense, the subject becomes a lot different, or is what I thought, because that's where you actually start to use Australian codes and you start to design stuff properly. So getting into it, you'll start to become very familiar with a lot of different terms, some of which you may have seen before, some of which you may haven't at all. So these are just some examples of some typical steel members, structures, terminology, and just because of these different structures, they behave differently. So for example, in trusses, right? Say you have a steel truss, okay? What type of forces would you expect in a steel truss? What do you reckon? What was that, sorry? Horizontal, vertical?
Shear.
Right. Would you expect shear moment?
Yeah.
Why is that?
Wind.
What do you know about a truss member? What is a truss member?
It's you draw it out. It's good.
That's alright. How is a truss member connected?
To the other roll joint. Where is it on the floor?
Yeah, on the floor. It has a roller joint, right? And then it'd be connected to a pin.
Yeah.
And then multiple pins after that, right? So those pins, do they carry a moment?
No.
Good. So there's no, or idealized, there's no moment throughout those structures, right? So they're purely tension and compression.
Yeah.
So different structures will behave differently, and then you do different calculations. So in trusses, really no moments, so to say. Can get some moments, but yeah. And then frames, right? You get moments, particularly at the connections and stuff like that. So different structures behave differently. And then when you do the course, you also cover connections, for example. So you do bolted and welded connections, and splice connections, and we'll go through those in a little bit. Okay, so for the course, you'll be referring to these codes and catalogs quite a lot. So the first one is AS4100, Steel Structures Code. And that basically outlines everything you need to know when it comes to designing steel, right? So that's this book here. If you want, you can have a look through it, pass it down. And got quite a lot of content. It's probably one of the bigger. But it basically tells you, gives you instructions on how to essentially design everything in terms of steel structures. And then the other one we've got here is the AS1170, which basically gives you ways in which to assign loads to steel structures. So basically, if you're designing something, right, say you're designing a steel beam, and you want to have a person stand on it who, say, weighs 100 kilos, right? Do you think that you would do an exact science and say, I'm going to design this steel beam to a person standing as 100 kilos? You're not, right? You're going to make that person seem like they're 130 kilos. So you need to increase your loads when you're designing, basically. And in saying that, you also need to make your section capacity less. So you need to act as if the beam that you're using is worse. So that code is basically for that. So I'll pass that around the world. And then the last one, which you'll be referring to throughout the term, is one steel. So you'll be using that quite a lot as well. And that just basically gives you all the information for the different types of steel profiles that you'll use. So I'm not sure how much you guys have seen before, but sections include stuff all this stuff here. probably seen before I-beams used in roofs and everywhere basically, and parallel flange channels, unequal angles, equal angles. These are all just examples of steel members, and this is the book or the catalogue that you refer to whenever you're designing steel members. Okay, so just to give a brief outline or overview of what the term will look like for you guys, this is sort of what it will look like. So you'll basically be covering these main topics. So tension design, compression design, flexural design, connections, and beam column design, which is basically kind of like a overarching subject at the end, which kind of encapsulates everything. Looks at like combined actions, so like what happens if you're both bending and have axial forces, all that kind of stuff. Are there any questions on the term outline or like what you're going to expect when it comes to these topics? Cool. Okay, and then I just wrote like some recommendations on how to study for this course, which I reckon, in my opinion. So obviously going to tutorials, that's a pretty obvious one. And I reckon looking at questions before class to give yourself an idea. And then one thing which is really important is having a really good set of notes, I think. Because a lot of the questions that you'll get in this course are very, very process driven, and they're quite hefty. It is very different to a lot of the courses that you've probably taken so far, like mechanics of solids, physics, maths. A lot of them can be like one number answers, and they might only take like a few steps of working out to solve. Whereas this course is a lot different in the way that you're designing like a whole like truss or a whole steel structure. So it might take you like a few pages of working. So it's very process driven type questions. So it's good to have a good set of notes that you can flow through when you're answering questions to practice, and then ultimately carry that forward into the final exam. It's very hard to practice the questions without notes. So have a good set of notes, and then once you get the notes out of the way, just practice questions. Just keep doing those. The more you get better at those, like the better you'll do. It's a calculation course, just like when you take concrete or fourth year electives like timber, or concrete, basically any of those subjects, calculation subjects, just practice questions, I think, are just the best way to study for them. Okay, so like types of questions you'll get asked. So this is not to scare you or anything, this is just to give you a bit of a jump start before you start the term, because this is what the questions will ultimately look like. You won't get this in week 1, these are from week 2. Week 1 will be like much more introductory. Talk about load cases, talk about like what are steel members, stuff like that. You'll probably do a bit of revision of 2303. Have you guys all done 2303 in here? No 2303? Cool. How about the rest of you guys? Have you done 2303? The structural analysis, yeah, structural analysis. Cool. So it'll be a little bit of that, but also don't worry if you haven't taken 2303. It's mostly also actually probably closer to 1300 than 2303 in terms of the statics that you do. Yeah. So these are some examples of questions. On the left is like a tension question, I believe. This is another tension question over here. So for example, this one here, it's like you've got two members connected to each other, right? And they've got bolts going through them, right, to connect them. So it's like a splice connection, if you will. If I were to put tension forces on that connection, what do you think are the ways in which that can fail? What do you reckon?
So if it's connected horizontally.
Yeah, so it's like two members like this, like connected horizontally, bolts going through them. How do you think that those two tension members could fail?
Isn't like a failure method?
Yeah, failure method, yeah.
It would just be shear.
Shear of what?
Shear of the bolt.
Yeah, really good. So it could be the shear of the bolts, right? So like if you were to pull tension on those members, right? The bolts could shear, right? Like the bolt head could just fly off or all together. What's another way it could fail?
Well, the members themselves.
Yep. How would they fail?
shear, or is that something else?
Not quite shear. Because like if I had like two members like this, right? Shearing would be like if I were to like put a point load on that member, right? But if I'm like this, right? And if I'm pulling the members apart, and say the bolts are like really strong, like infinitely strong, right? So they're not going anywhere. They're fine, right? If I pull those tension members apart, what will happen if the bolts are just really, really strong? What will happen to like the bolt holes, do you reckon?
Well, they'll get bigger, go expand.
Yeah.
Or just form a crack.
Exactly right.
Okay, yeah.
Perfect. Yeah, you start to get cracking, right? Has anyone taken like Maths 1101 as well? Just doesn't really matter if you have or haven't. Okay, perfect. You know, like fast crack propagation, right? No, that's all right. Like notches, all that stuff. Basically, like it will take like the path of least resistance, right? It'll go like straight down. Like so, say for example, like you have like a member like this, right? And let's say it's got like bolt holes just there, right? And it's got an axial force this way, right? Pull that way, and then what you would expect, right? One of the failure modes would be to just have cracking throughout the section, right? Through the bolt holes. So it'd be like something like, right? Perfect. And then another way that that could fail, right, is not just like fast crack propagation, but just like yielding on gross section as well. So like say say you didn't have bolt holes, or say you were just like tensioning this member, right, and then you could just have like that fail in itself, right? But if you have bolt holes, or say the bolt holes were like this, right, you might have yielding on gross section first, but I'd still expect that to go through bolt holes, or maybe something like that if they're a bit closer together. Right. Okay. So I'll switch it back to this one.
Okay. Get you to use the other markers, but
Yeah.
let's see.
Okay, so yeah, just so you guys know, this isn't to scare you. This is just to let you know what the questions will start to look like in week 2. Very process driven. It looks like a lot of words, but once you break down the process, it's just about like getting your loads, and then using the loads to get your forces, get reactions, and once you do that, you basically just follow a process, which is basically in AS 4100 to work out the like tension capacity, compression capacity, see whether it's failing or not. Okay. So here's some more examples of workshop questions, which will be later in the term. And this is just to give you an idea, that's all. Ooh, that one's messed up a bit. This is like some examples of assignment questions that you might get asked. So they generally look like a bit like this. Once again, very similar. So this is basically every type of question that you'll get asked in this course. It's no like assignments, no writing, unless they might have changed it, but I don't think so. All the questions are going to look like this. Workshops, assignments, final exams. Right.
Just a bit zoomed in.
That's all good. Okay. So now I'll move on to this, because in this is the first course, right? Where you probably, well, has anyone seen this before? This type of notation that I've got here? Cool, no worries. So this is probably like the first course, and you might have later courses down the track where you do this type of stuff. But this is where you get into like engineering design, right? Because what this is basically saying, right, is your section capacity has to be larger than the force that you're applying, right? It's a pretty basic rule, but that's what it is. That's how we design in engineering, right? We make the section seem worse by applying a reduction factor, this phi factor here, it's a reduction factor, and we make the forces seem more exaggerated or worse by increasing them using load combinations. We apply like increasing factors, if you like 1.2 or 1.5. We increase the forces and we make the section seem worse. Yeah. And so then you'll see that for different types of things. So for example, like tension capacity, compression capacity, section capacity, member capacity for like bending, all different kinds of actions, forces, ways in which, yeah. Is this okay so far? Is there anything you want to say? Okay, it's good. Cool. So yeah, so all I'm trying to say is with this is like kind of the first course, we're doing engineering, and just remember this is like the main principle, right? You've got how much your section, how much your tension member can carry, and how much force is being applied to it. So you're making that force seem worse, and you're making the section also like you're making the section seem like it can carry less load. If that makes sense. Does that make sense to everyone?
Carrying less load.
No, so making the load seem more. So exaggerating the load, multiplying the load up by like maybe 1.5, and then making the section seem worse. So like you might say, oh, it's like a 150 mil tall I-beam, but you might say, oh, I'm gonna multiply it by a factor of 0.85 to make it seem worse, like it can carry less load.
Okay, yeah.
Does that make sense?
Yes. Yeah.
Okay, cool. If you get, yeah, do you want
No, I was
to?
just gonna say that. So where this is all coming from, right, is what you've done in structures so far is analysis, right? So basically what that is if you get given a structure, right now what you know how to do is how to apply loads on it, and you know how to do statics to calculate, oh, the force in this thing is 5 kilonewtons, in this is like 10 kilonewtons, like a truss or whatever, right? So that's what you know how to do now. Structural analysis 2303 also covers that in greater detail, but that's basically what it is. This is the first course where we're looking at making sure the structure that you're designing can withstand that force, right? Because it's one thing to know, it's one thing to calculate that, oh, this thing is going to have 5 kilonewtons in it. It's another thing to be like, wait, will it break if there's 5 kilonewtons inside? That's the other question, right? So that's design. So analysis is the first part, which you've already covered. Now it's design, and each material has its own subject, okay? Because it's a different design rule. So you've got steel structures, as Will was saying, eventually you've got concrete, etc. And what he had on that slide earlier.
Oh, let's get it up. Sorry. Yes.
So what Will was just explaining earlier is this is how we figure out if the material can take the force that's applied, right? So N star is whatever you've learned from statics, from Eng 1300 from 2303. That's what you've been calculating so far, right? But as Will was just explaining as well, you make it larger than it is. So for example, if in your statics you do your calc and it says, oh, it's like 5 kilonewtons, you might increase it a bit, okay? You'll scale this side up. And this side is how strong the material is. So it's the capacity. So like if this, for example, is 8 kilonewtons and the material can only take 7 kilonewtons, then it'll fail, right? But if this 8 kilonewtons and that is 10, then we can pass it and be like, oh, it works. That's the basic thing here. And this 5 factor here is a reduction factor, as what we were saying. So for example, like if you've got any steel member or anything, in this course you'll learn how to calculate how strong that steel member is in different ways. But not every steel member is perfect, right? Sometimes there can be manufacturing defects, sometimes the steel is weaker in some area, it wasn't rolled properly, whatever it is, it's not always going to be perfect. So that's what this 5 factor is doing, is it's just reducing it for safety. So you take how strong the material is and you reduce it, and you take what the load is going to be in the material, you increase it, so there's like 2 levels of safety. And as long as this side is larger than this side, you're Gucci. And that is like that's just basic. That's called limit state design, and that's inherent in every material you study. Yeah, so that's basically.
Oh, thank you. Thanks a lot. Yeah, it's perfectly said. Limit state design. So when you do your N-star, right, those factors that I was talking about, this is what you'll be using a lot throughout the course. So these are the load combinations which you'll be using for your end star that Prash was talking about. So there's two main load combinations. One is for dead load and the other is for live load. So if I've got a structure, say, and I'm say it's a building, right? Say it's this floor, right? And say it's got maybe not this floor, but say this floor has like steel joists running underneath it, steel beams, right? And I want to design those steel beams, right? When I do my end star, right, when I calculate my end star, I'm calculating the dead load from the chairs, the tables, the materials around, concrete, all that kind of stuff. I'm calculating the dead load. And so when I calculate that dead load, I need to multiply it by a factor, right? So if I'm, say, calculating N star for dead load, I'm going to multiply it by 1.35, okay? Now the other load combination, the other load case, which is like the most common one you'll do in this course, because from AS 1170, wherever it was, there's heaps of load combinations for wind, for snow, for serviceability, like calculating deflect. There's heaps of load combinations for basically every load that you can think of. But these are the main two that you'll do in the course, dead and live load. So if I want to calculate my N star for live load, then I take my G. By the way, G is for your dead load, due to gravity, right? And Q is your live load. So when you calculate your live load, you still have to take into account your dead load because, I mean, the structure is still there, right? So when you're calculating your load combinations, these are the factors that you'll be applying to your G and your Q. Does that make sense? Is anybody not too sure about that? It's totally fine if not, yeah?
So when you design, do you take whatever's the worst case for the load?
That's exactly right, that's exactly right.
But you still have to calculate.
That's exactly right, yeah. And you'll do that as well in the industry, like in design. You'll always take the worst case and you will definitely calculate multiple cases to see which one is the most critical, the worst. Often this one will be your governing case throughout steels. I say that lightly because you never know. This still might be your governing case, but G has to be 10 times worse than Q for this one, unless there's a. But yeah, those are your two main load combinations which you'll use in this course, which basically just amplify the force that's being applied and make it seem worse for that limit step design. Anyway, yeah, cool. So that's all for that presentation. That was just like an intro to get you started on the course for steel. If you understand that, I feel like it's actually really easy to understand everything else because everything else is literally just numbers, formulas from the code. It's a very process-driven, step-by-step sort of way of answering questions. So I'll go into that now and talk about the first topic, which is tension design. So just going back here, I'll just go through tension design now. Okay, so I'll probably do this on the whiteboard.
Just while you're getting that ready as well.
Yeah.
Load combinations, even in timber, when Will and I were taking it, and Prash was teaching
yeah.
it, load combinations are still one of the hardest parts, like, to understand. So this shit doesn't get that much easier. I mean, you learn it in week 1 of steels, but it's good to know because you'll use it throughout.
Yeah, I feel like this is like your first proper introduction to load combinations. But if you're interested in into actually going into engineering design, you'll use this stuff all the time. So it will just be like common practice, second nature to you.
Maybe
Should you do an example or choose?
So that's good.
Well, I think we can do it like conceptually.
Yeah, true.
And do you want to put the lines down on that side?
Let me do. We were doing this earlier. Oh yeah, I can see there's a bit of shine on. Hopefully it's.
Is there any questions so far or anything? By the way, like, I know it's very cliche, but so you can't questions, seriously ask anything. It's not on the word, you can ask any questions.
I can't make that any bigger, hopefully it's fine. If not, yeah.
Okay, cool. So I'm just going to go through the first topic. That's all. So it's just tension design. So you cover this in week 2. Week 1 will just should be an introduction, or from what I remember. So I'm going to go through the topic which is taught in week 2, which is just tension design. So this is basically just for designing steel tension members. Okay, so for tension design. So remember when we talked about the 2 members being pulled apart? So if we forget about the bolts for a second, does anyone remember what the 2 failure modes for the tension design was? Yeah.
The shearing of the bolt, cracking.
Shearing of the bolts, but let's just forget about the bolts for a second. The cracking was one, right? And do you remember what the other one was?
The cutting of the beam, like.
Perfect. Yeah, nice work. So exactly right. So one failure mode is just like yielding on growth section of the member, and the other failure mode is the cracking, like you said. So I'll just write those on the board. That's a bit better. Okay, so this is the first one, first failure mode, right? Yielding on growth section. So this is like your first capacity that you have. Remember from the PowerPoint? N star less than phi NT. So for phi in this case, we use 0.9, and you can refer to that in the AS4100. So that book that I was passing around before, has anyone still got it? Oh yeah, awesome. Is it right if you just pass it? Oh, thank you. Cool, so what you'll do when you're answering questions, right, is you'll go to this book. Now, you probably have a PDF on your computer or whatever. By the way, do you guys all know how to access Australian standards for uni? Okay, no worries. Have you guys heard of Sci Global? Okay, I should probably show them that.
Do you want to do that at the end?
Yeah, I'll just do that at the end. Anyway, but you just get a PDF of the standard. Anyway, so you go to the table, table 3.4. Yeah, here, right? I don't know if you guys can see that. It's table 3.4. It's basically just got all the factors for the different types of ways in which, different failure modes, different types of forces, compression, tension, bending. Okay, so yielding on growth section. The other failure mode, like we talked about before. Okay. What do you guys notice different about the failure mode 1 and failure mode 2? Super quick, what do you reckon? Any differences? Or what are the main differences?
0.5.
Good, true. What else?
There's a K factor on the way.
Nice, yep. Anything? Yep.
That implies takes more force for it to be.
Not necessarily. More force or less force?
Less force.
Why do you reckon less force?
For case 2.
Yeah.
Oh, sorry, more force.
Not quite. But it's good, but less force. Because bolt holes, right? What are they going to do to the section? Oh, sorry?
The bolts.
Yeah, the bolts. But what will the bolt hole? So for the connection, right, you're going to have heaps of bolt holes, right? And by the way, it might like look like bulge.
That's especially not there.
I don't know if you can see the but it might be like a whole group of them, right? Or it might be even like stagnant, like something like that, right? what are the bolt holes themselves going to do to the section of the beam? Say this is like a beam, right? What are the bolt holes going to do? Good, they're going to reduce the area, right? They're going to make it less. They're going to make the section ultimately weaker, right? So do you think it's going to take less force or more force to break this if it's got bolt holes?
So area will be a small number.
Good, exactly right. So your NT is generally going to be less, right? Less force required. So it's probably going to be a governing failure if it's bolt holes. Okay. Now, AN. So, what do you reckon AN is versus AG?
The G is the gravity and it's more force.
What was it, sorry?
Subscripts like G is
G?
the gravity.
Oh, good guess. Not quite though. Not quite.
Is the N for normal force?
Good guess again, but not quite either. Have another guess though, right? This is for bolt holes, right? So you're gonna have a different area, right? Like, remember this is A is obviously for area, right? So we're talking in terms of area. What's going to be the difference in area when we talk in terms of yielding on the whole section versus yielding when there's bolts? When you have bolt holes, what do they do to the area?
Reduce the area.
Reduce the area, right? So what do you reckon this is called? Net area, that's all.
Oh, okay.
This is called the net area.
Sure.
So this is the net area, this is the gross area, right? So if you have a section, a beam section, right? When you talk about yielding on gross section, you're talking about the whole section. It's alright. Yeah, and then bolt holes, right, you're going to reduce the area, so net area. Alright, net area. Okay, so these are basically the notes for tension design. Now, one thing we haven't really covered is calculating KT, which are, net cross-sectional area, which I'll also go through. Does everyone have that down? Because I might just rub this off. This is, so first one, when we calculate for the net area of the section, right, is for staggered holes so far. So I'll get to, unstaggered holes when it's straight line. When it's staggered, like this, I'll get to that in a second. But just for now, for staggered holes, like when it's like this, right, your net area of the section, right, is just going to be the area of like the section. So this is just like, if I took a sort of a section through there, right? So now I'm looking into the section, right? Then I'm going to have this, aren't I? These are going to be the bolt holes, right? And the thickness of these holes, right? Well, that's just the thickness of the section, isn't it? T, right? And the height of these, right? They're just rectangles, right? It's just the, what is that actually? What do you reckon?
So
What's this dimension here? That's all. This dimension.
the diameter.
Perfect, right? Because it's basically just, it's that, isn't it? Right. So it's just the diameter of the bolt holes. Now, we also plus 2 mils for bolt holes. I think that's just because of the threads of the bolts, right? So it's just a bit of like extra tolerance when you're calculating that area. And then there's a bit of a special case for base plates as well, where you add 6 mils. I think that's just because bigger bolts generally.
That's also, that has to do with the installation method. So when you have a plate and you've just got a normal purpose, general purpose bolt you're applying to it, first you take the plate, you drill a hole in, right? But obviously the hole won't be the same diameter as the bolt, because then it may not fit. So general use case, your bolt hole will be 2 mils larger than the diameter of the bolt. But if you're using it for a base plate, generally you'll have a more hefty bolt that will generally be larger. And generally base plates as well will be drilled into or anchored into concrete because you're using them like as a base, right? And because of that, you'll have a hole that's about like 6 mils. 6 mils is safe, but 6 mils larger. One of the other reasons, of course, is also whatever you're attaching to your base plate, which is maybe a column, for example, when you're looking at members on the floor, they generally have the largest load on it, right? Because they are withstanding the load of everything above it. So they are subject to more movement, right? And so what you don't want to have is a very tight system at the bottom that doesn't allow some slack from a construction point of view. So generally, that's why you'll have a +6 mils basements. But everything else, you just add +2 mils.
And but generally as well, like with like bolt sizes, like in the course, you'll often see them like there's like M12 bolts and stuff like that. The 12 there just represents the bolt diameter. So when you want to find out the D, that's just 12. Okay, so I'll do now say staggered holes. Okay, so say you get a section like this, right? And you might have just staggered holes, or you might even have like both staggered and unstaggered holes. So in that case, you also have to calculate both. But say just for staggered holes, right? When you calculate staggered holes, you use this formula. So what I was trying to say before is like, I feel like as long as you understand the concepts behind everything that's going on, you're halfway there, or you're already there, because the rest is just following formulas. So for this, right, for staggered holes, this is your formula here. SP is perpendicular to your load. So say this is a tension member, right? So you have force going this way, or that way, whichever way, right? So for this one, so you have like, that's going to be the perpendicular to the load. So that's going to be like your SG right there, okay? That's like the perpendicular distance between those bolt holes. Does that make sense? Cool. And that one just there, that's your SP. Okay? And that's it. That's how you calculate your AN. Then once you've got your AN, you just calculate your NT, right? Back to that formula, NT is equal to 0.85 KT AN FU. What's FU? Pardon my French. What is it? Does anyone know? What was that, sorry? Oh, very close. Not quite. Perfect. What's yield strength? How do we represent that? What's that?
Yeah, the letters.
Yeah, sorry, the letter, yeah. Yeah, F, or you might be thinking sigma, like this one. Yeah, sure, in like, that's your stress, right? So like yield stress when you do, Young's modulus and all that. But when we write it in steels in design, we write yield stress as Fy. So when you see Fy, that's yield stress. When you see Fu, that's ultimate strength. Which one's higher? Very good, right? Because it's like your curve, yeah. When you've got steel, right? It's yielding around like here, and like maybe work strengthening, and then like ultimate failure there, right? Cool. So, and by the way, why would we use ultimate stress here in this case? Why not? Because in the other one, right, in yielding on gross section, we use yield stress, right? Why do we use yield stress up here but ultimate stress down here? What do you reckon? Any guesses, any clues?
So related to limit state design?
Good guess, but no, not really. Let's think about it, right? If I'm pulling a tension member, right? Say I've just got like a steel beam, right? No bolt holes, right? So I'm expecting it's going to just fail by yielding on gross section, right? When it yields, right? Say it's like I'm pulling this member, I-beam, whatever, or channel. I'm pulling it. What will start to happen? Is steel a brittle or a ductile material? Perfect, right? So what does ductile mean?
It'll stretch.
It'll stretch, perfect. So it'll start to yield. So before, like the point of failure, right, is that stretching. It's that plastic deformation, right? So that's why we use FY for yielding on gross section, because the moment it fails is when it's stretched and it won't go back. That's where we draw the line with failure. When I've got cracking on net section, what's happening there? It's cracking, right? The whole thing's just gone like bang, fast crack propagation, right? So the steel actually splits, right? So that's when you're there now. Is that crack will just go straight through the bolt holes and just completely break the material. So that's why you're using ultimate stress there, not real stress. Okay, that's mostly it for tension. I think. Was there anything else for tension? I think that's basically it.
Just on a bit more on that, you can think about the difference between yielding and ultimate. Yielding is, think about it as it hasn't separated yet, right? So the steel, if you take it and you stretch it high enough, eventually you'll start to neck, right? So you'll kind of, like, if that was your depth, you'll start to do that, right? As you stretch it out, so it becomes like bubble gum. That's yielding. So you can think about that as yielding, but it's still intact. Ultimate is when it just snaps, right? And of course, like steel first yields and then snaps. So therefore, the strength to yielding is less, and if you kept stressing a bit more, then it'll snap. So the first failure mode for yielding of the gross section is just looking at how much force does it take for your steel section to become bubblegum, right? And then net section is basically looking at cracking specifically, and that's why we use it.
But so in that case, what's like the difference between the ultimate strength and failure? If like on a graph, like there are two different spots on the graph, but you're saying that ultimate is when it actually cracks.
Okay, so the question now is what do you mean by failure?
Like when on the graph you draw like X, is it
Like when it breaks?
You mean like
yeah,
that?
yeah.
Yeah, okay.
And like the difference between that and the hump, which is the ultimate strength.
This is like this point here, the difference between that point and that point?
No, the top.
Oh, right. That's work hardening, right? I think that's when you keep on straining the steel or whatever material, and then it actually gets stronger because of like the crosses between the dislocations. So like when you stretch the material, sometimes like if you stretch a material past its yield point, sometimes that material can actually get stronger, even though it's like gone through plastic deformation. Like so say you like stretch steel, it's gone like it won't go back to its original shape, but it might actually be stronger after you've stretched it a little bit.
Yeah.
Just because like you get like all these dislocations of like molecules and stuff like that.
The stronger just meaning it'll take more load. Like once it's yielded, you can keep stretching it because it hasn't broken yet. Like it's not snapped yet, right?
Sure.
So you can keep increasing the load on it, and that's why it goes to the hump on the top, and then eventually it'll snap.
Oh, okay. Yeah, sorry, I was like imagining, like, because I've heard that as the UTS, and I was sort of like imagining it as the ultimate strength, but it's not.
Yeah. No, that's your ultimate strength. Ultimate stress.
In this case, ultimate means like fracture.
Yeah, ultimate means like it breaks.
Fracture.
Okay.
So that's where it breaks. That's where the material actually snaps off. Yeah.
Cool.
Yeah.
Alright, that makes sense.
Cool. I should, yeah. That's okay. Yeah, I think that's all for tension. Was there any questions for tension at all? Like, remember, no, it's cliche, but seriously, no such thing as dumb question. Ask like anything. All good with tension? Okay, cool. Should I go?
Which week we're on? It's all week one.
Yeah. This is pretty much like week 2. I think
Yeah.
it covered in week 2.
Yeah.
Oh, yeah.
Week 1/week 2 / week 3 maybe. Nah. I think it's like
One.
yeah.
Should I take a photo?
Yeah. Thanks. Should I go through? Just think about time.
Yeah.
Was it?
Maybe you do the rest like concept.
Yeah.
Should we give them a break?
Yeah.
Yeah.
Sounds good. They like 5 minute break.
Yeah, you guys want a 5-minute break?
Oh, you can get started while then.
I might get some more.
Yeah, bro.
Alright. In the interest of time, I think what we'll do is conceptualize the rest of the topics. Now, I think it was really good what Will did because that was meant to sort of be like a head start for you guys because a lot of that's going to be like one of the first few things you learn, right? Just the 3 important things to take note of from what Will spoke about before. 1, load combinations, right? And if you have any questions on load combinations and stuff, we can go through it after. The second thing is tension design. Within tension design, those are the 2 parts. You had yielding on the gross section and fracture on the net section. That's literally all it is, right? And with that amount of information, you have enough info to be able to do the first set of workshop problems. Okay, so hopefully when the lecturer does talk about it when it starts, you're across what he's talking about. So conceptually now for the rest of the course, right? These are the main topics you're going to learn, right? So the first thing we covered is tension design. The second thing that we're going to be doing is compression design. Oh shit. He ran away. Oh, Henry.
Oh, yeah, this is called.
What should I be doing? Oh, sorry.
It's no, it's
Like,
this thing. Very fidgety. I'll move this closer. For some reason, that's closer it works.
yeah.
Fuck. Fuck. Okay, it's back on.
Thank you.
All good.
Okay, these are the main parts of the course. Okay, what Will just covered was the first part, tension design. Okay, now it might seem obvious what the rest of those are. I'll go through now. So the second thing is compression design. Compression design, obviously, figuring out how strong the steel member will be in compression. Now, within compression design, there's a couple of things that we will be looking at. The first thing within compression design is crushing failure. Okay, or rather section failure. And the next thing is buckling failure. Okay, those are the 2 main methods of failure. Now, one thing you will realize that's happening in this course over and over again, basically, is how do you calculate how strong something is going to be? Right? If you think about it, you want to figure out if the steel member is going to be strong enough to take tension, if it's strong enough to take compression, if it's strong enough to take bending. Where do you start? How do you know how to calculate that thing that you're designing for? The most important thing is to think about how's it going to feel. Right? So what's the failure mode? Within each of these things, when you're designing for tension, for example, there were 2 ways it could fail. Right? One is if the entire section yielded. The other was if the net section fractured through the bolt holes. Right? So there's 2 formulas for that. And then, okay, let me give you an example. Right? So going back to what Will spoke about earlier, if you have a steel member that has a, let's say you use the formula for gross section yielding. Okay, you calculate it, and your load is 200 kilonewtons. Okay, just remember that, right? 200 kilonewtons. Now, for the net section fracturing. So you've got your bolt holes, you do the staggered thing, and then you calculate how much force it's going to take to snap that. And you calculate 150 kilonewtons. Right? So the first failure mode takes 200 kilonewtons for it to happen. The second failure mode takes 150 kilonewtons to happen. Which one governs? The 200? Why?
Because you see that it takes more force to want to give a scenario, set a scenario where that it can withstand more than 200.
Okay. So let's run that thought experiment. I picked that thing up now physically, right? I know at 150 kilonewtons, if I pull it apart at 150 kilonewtons, it'll fracture.
Wait, no, it has to be less than 150.
Exactly.
Yeah.
Right? It's the other way around. So that's the thing you've got to remember. For like we say, look at the worst case scenario, right?
Yeah.
That's when you're looking at load combinations. So like when you're looking at load combinations, right? You're trying to figure out what's the worst case that'll happen, right? What's the highest load that this thing will experience? That's what I want to know. But when you're looking at strength, capacity, which is the other side of that arrow, when we're talking about real estate design, we are interested in what is the lowest exactly. What basically at what lowest load will it start to fail? Because that's the governing failure mode, right? Because if the thing is if something's already going to happen at 150 kilonewtons, I wouldn't care what's going to happen at 200 kilonewtons. The thing's already gone.
Sure. Yeah.
Right? So that's what you got to remember. So this idea behind failure modes is basically informs everything in design, right? So for example, in compression now, there's two methods of failure. One is section failure, section level failure, and the other one is buckling failure. So I just want to talk about those two briefly now. So let's have a look at compression design. Okay. Now this is good. This is going to look like a lot, but I just want to simplify it here. I'll share with you guys the OneNote notes for this, so you have all the formulas and you can follow along when you watch the lectures. But basically, when you're looking at compression design, there's two things like I mentioned. There's section capacity and there's member capacity. Section capacity looks at the cross section failing. Member capacity looks at the entire member failing globally. Okay. I think what would be better. Sorry, do you mind if I move the screen? Okay. Alright, so let me just draw it out here for you, right? Let's say you have this short little stubby piece of steel, okay? And it's on the floor, right? And now you've got a mechanical actuator on the top and you're just squishing it down, okay? When you have something really short like that, what do you think is going to happen? It's going to squish. Right? You take a piece of steel, put a short piece of steel under a metal actuator and you push it, it's going to squish. That squishing action is, it might look something like that. That squishing action is basically called section level failure, right? Because it's local. Section level failure is a local failure, right? It happens only at one point. Okay? So, how do we calculate the strength of that? Really simple. Again, you look at the cross section area multiplied by the yielding strength of steel, right? In fact, it's the same formula as yielding on the cross section, because yielding, by the way, can happen both ways. You can stretch a piece of steel and yield it. You can squish a piece of steel and also yield it, right? Yielding is just an instability of the material. So that's section level failure, right? The key characteristic about that is it's only one section. Now, so it's a local failure. But what happens then if I have a really long piece of steel and I apply a load like that? Okay, what do you think will happen now? Think about a ruler, right? If you have a ruler and you orient it in a particular direction and you push on it ever so slightly, the entire thing is going to start to bend, right? Now I want to use the word bend carefully because, in fact, I don't want to use the word. Basically what will happen is it'll buckle, right? When you push ever so slightly on it, the way it'll feel now is it will do something like that. Okay? So this failure is buckling failure. And the first one is a section failure. Okay? This is also called a member failure. Why are we calling it a member failure? Because it's global. It happens across the entire member. Okay? So, of course, there is a formula to calculate this, and there is a formula to calculate this. Right? Now, you can see how I drew it specifically longer here, and then this one is shorter. That's because whether something buckles or not depends on how slender it is. Right? And the opposite of slender is stocky. Right? So if something is super stocky like this, that's probably how it's going to fail. The more slender an element is, the more likely it is it will buckle like that, like a ruler, right? Basically. So now, what is stocky and what is slender, right? There's obviously, we've got to come up with some rules as to define how do we know if something's stocky or slender. So when you're looking at, and sometimes it can be difficult to define, right? What if you have something of intermediate length? What if it has a large cross section? Like, how do you define what stocky and slender is? So what you generally will do is you will work out the formula for section failure, and you'll work out the formula for member failure, and then you'll see which one governs. Okay, so I'll give you another example. Let's say section failure, you calculate it, and it's 450 kilonewtons. Okay, let's say buckling failure happens at 150 kilonewtons. So 450 here, 150 here. Which one governs? The 150. Right. Why? Because that's what's going to happen first. Right? So that is, in a nutshell, what you're trying to do. Right? So you use each formula and you assess a different failure mode, and then you pick the smallest one. Right? And then, is that design action or is that strength? Yeah, well, I'll go back to this. Remember this formula here that Will wrote just now?
Yeah, not sure I said the word.
Yeah.
Action effect.
Right? So remember, the left-hand side is what the element is experiencing. Okay? The right-hand side is the strength. Correct? So, just now that example I gave you, 450 here and 150 here, what is that? Is that the left-hand side or the right-hand side? That's the right-hand side. Okay, so this side is the strength side. The left-hand side is called design action. Design action means what force you're applying onto it from the structure. Okay? So, imagine, I'll give you the real life context of this. Let's say this column here, that we have this 450 kilonewtons and 150 kilonewtons, those are the two strengths of the column, right? Let's say that's a column in a building. Okay? Finding out what the design action is and what the strength is are two different tasks. Okay? So the design action has got nothing to do with the strength of the column. It has everything to do with what is sitting on that building. Right? Because whether you put a concrete column there or a steel column there or a timber column there, that thing is going to experience that amount of load. Right? Because of all the crap that's sitting on top of it. So design action is what it will eventually experience when you install it. This only has to do with like how strong the material actually is, or how strong that column actually is. So if you're going to use a steel column, what is this number? If you're going to use a concrete column, what is this number? Timber, what is this number, right? So this number changes depending on what you're using. And you can think about it as the only way to figure it out is you're doing a study on the material itself. Okay, so this thing here that we talked about is a study of the material. Right? We are saying, oh, at 150 kilonewtons, it'll fail through buckling. At 400 kilonewtons, it'll fail through section failure. That's a study of the material. So once we calculate that, we know, okay, this particular column, at 150 kilonewtons, it'll fail through buckling. Right? So, for the right-hand side, okay, once we go through our different failure modes, what do we pick? The failure mode with the largest load or the smallest load for this side? So for strength, right? Are we picking so remember, when we're looking at strength, we're looking at different failure modes, right? Yielding, fracture, whatever. Buckling, section failure, whatever, right? What do we pick, the smallest one or the largest number? Smallest. Okay. What about this side? Right? The question tells you during winter there's going to be this amount of snow. On a really windy day there's going to be this amount of wind, right? On a really crowded day there's going to be this amount of live loading. So which one of those do you end up using for this? The smaller one or the larger one? Largest. Exactly. So that's the key thing to remember is on this side you choose larger. For this side you choose smaller. Right, so for the right hand side the smaller one governs. For the left hand side, you can see that. For the left hand side the larger one governs. Okay? Alright. Yeah.
Do you think that like as the right hand side is more of like what's actually happening, like more of the experimental, but the
Yes.
left is like the theoretical?
Yeah,
The
so
advanced assessment of materials.
right. So the way I look at it is the right hand side is very much like experimental, right? It's like, oh, if I took that and I put it in a lab and I tried to smash it, what's going to happen? What feeling was I? That's the right hand side. The left hand side is once this material is installed, what forces is the building going to throw onto that element, right? That's how I think about it. So design action on the left hand side is really what will it be experiencing in real life, and then the right hand side is how will that thing react to what you're going to throw at it. That's basically what it is. Okay. Any questions on compression so far? Understanding the basics behind the two failure modes. Yeah.
If you say like that still
Yeah.
you have you have like connections in the middle.
Yeah.
Then would you calculate? Then would that just become like you would calculate sections by sections? If you say
That's a really good question. So what you will end up doing, right, is right now this column here. By the way, that's the other thing you got to know. Terminology. Beams are always horizontal elements. Columns are always vertical elements, and that will never change. Okay. So strictly speaking, when we're talking about columns, we're talking about the vertical elements, pillars, beams, joists, whatever. Those are all horizontal elements. Okay. Now, to answer your question earlier, this one is restrained on two ends. Right? This thing is restrained on the bottom and in the top. Right? So there's only two restraints. But if I were to take that same column and restrain it, so that's a column, right? And let's say I restrain it here and here. Okay, and now if I apply the load, what will happen? Alright, so that will probably do something like this. Right? Because it's pinned at those points. Right? So it won't exactly buckle this way, it might buckle like this. Right? So which do you think is the stronger one, left or right? This one, right? This one's the stronger one. It's going to take, if you release the pins, obviously, then the whole thing becomes a bit more unstable. Right? So, in the formula for buckling, which you'll eventually learn in the lecture, one of the elements in that formula is length. Right? The larger the length, the lower the buckling capacity. Right? Because the longer something is, the easier it's going to be to bend it. Right? Make sense? Okay. So, in this case, length will be the entire thing, right? In this case, the length won't be the entire thing. The length will be the distance between the restraints, right? Because the buckling is only happening across this distance. Okay, so that's how you can clarify that. That's how it's actually being strengthened. In the formula, you'll see, right? L is a huge number here, which means the capacity will be low. But when you reduce, they're inversely proportional. So when you reduce L, the capacity increases. Okay, that's buckling in a nutshell. Make sense? Any questions? Yeah.
What's an example of a restraint you might put?
Okay, so a restraint would be like, let's say in a building, right? You've got a tall column that runs across 3 floors. Okay. Each floor might have a beam that's connecting into the column, right? bolted in here, bolted in here. Those beams act as restraints, right? Sometimes it can be, any other bracing element, for example. If you've got a brace that's coming in to connect across the halfway mark along a column, then that's also a restraint. It can be like a bunch of different things. As long as you look at something and you realize that that thing that's connecting in is stopping the movement from left to right, that's a restraint. Okay? And that's also another tricky thing that you'll start to figure out in the course later on, in the later weeks of steel, is you need to be able to look at something in real life and decide what kind of restraint is it. Because there's different types of restraints. Okay? But anyway, I won't bore you with that. That's later on in the course. Okay, makes sense? Compression makes sense? Yeah? Okay. Now, as you can see here in this example, we are only looking at one column, isolated. So very much experimental, right? I've built a column, now I'm going to crush it, and these are the shapes I'm going to see. Of course, in a building, it's not really going to be like that, because in a building, you're looking at it at a 3D context. Okay? So let's talk about a real life building now. In 2D, a frame of a building might look like this. Okay? Let's say this is a 2D frame of a building. These are columns, right? Now, very much so for this course, the way we'll look at it is we will separate each story as its own column. Okay? So for example, this is column for level 1 for ground floor. This is column for level 1, this is column for level 2. Right? This is the beam, this is the beam. Get the picture? Okay. Now, why is this important? Why do we care what's going to happen in a building, right? So if we look at the previous example here, as you can see, the deflected shape matters a lot, right? Like I drew for you the deflected shape. This is how it looks like when it's deflected. Okay? This is how it looks like when this deflects. The deflected shape is really important because points of contraflexure, which means when the deflected shape basically switches from one side to another, a point of curvature, right? Those are the points where you take your length. So that's a point of contraflexure, that's a point of contraflexure, that becomes the buckling length. Over here, there's only 2 points of contraflexure, top and bottom, right? So deflected shape matters a lot because that gives us what the length over which it is buckling is. Okay, and it may not be very obvious. Well, here it is. But let's talk about a real life building then. In this frame here, right? Let's say I apply a load this way. Let's say there's wind. Okay? And let's say I'm interested in this column here. Okay? So the question, let's say the question asks you, design the strength of this column. Maybe I'll make it easier for you. Maybe I'll switch this to, since it's a compression topic. Okay. Let's say there's a load over there, right? The question then becomes, how will this column bend or like deform based on this load on the top, right? So if we imagine the deflected shape for this, maybe, you might end up with something that looks a bit like this might bend, say this way, this might bend that way, something like that, maybe, right? But of course, in a real life building, you don't only have loads in one direction, you'll have this inclusive with wind, etc., that might be coming from different directions, right? Okay. So let's say, I'll leave it as for now. Okay, so that becomes the deflected shape. Now, the thing is, this column is fixed in with this beam, fixed in with this column, that's fixed in with this beam, that's fixed in with this thing. So in reality, this thing is not operating independently, right? This thing will deform based on the deformation of the rest of the building. Okay? In the previous example, I'll give you a really simple example. The bottom is imagined as a pin, and the top is imagined as a pin. That's a really, really simple example because it'll just bend perfectly, right? But when everything here is interconnected like that, like this, in a real life building, that's not how it's going to deform, right? Because the deformation here is linked with the deformation width of every other element, okay? So for example, the way this beam bends as well, right, will affect the deformation of this column, right? So thought experiment here. If this beam is really, really stiff, imagine you put this huge chunk of steel over here, okay? And this is like a really thin piece of steel. This is a really thin piece of steel, okay? This beam will be acting as a very, very good restraint for this, right? Okay. Now let's switch it. Imagine this is really stiff, this is really stiff, and this is really weak. Will this beam be doing anything to restrain this element here? No, it won't, right? It's quite easy to see that, right? If this was like very, very thin, and this was really stiff, and this was really stiff, then when the whole building deforms, this won't be doing anything to stop this whole thing from moving. It's just going to move, right? You see that the terms I brought up just now, I talked about stiffness, right? So how strong or how this column will deform is based on the stiffness of the column above and the stiffness of the beams that are framing it, right? And based on the stiffness of, basically the stiffness of the members around it, right? So this column runs between the bottom node and the top node, right? If I know the stiffness of this, if I know the stiffness of this and this, there's nothing here, but if there's something coming in here, it includes the stiffness of this as well. If I know the stiffness of each of those things, I then know how stiff this point is, right? I can then also know how stiff the bottom is. And if I know the stiffness of these two nodes, then I can estimate how the entire thing is going to bend. Okay? The art of doing that is what gamma method is. Okay? So what is gamma method for? We use it for compression, okay? But it's a tool to basically calculate what the effective length of an element is in a more complicated structure like this. Okay? If it's a simplified structure, there's only one column, you're applying a load, then you don't have to use the gamma method. But the gamma method basically is teaching you how to calculate what the effective length is for a more complicated structure like this. Okay, so for example, let's say I'm interested in this column here. Okay, give it an example. Let's say I'm looking at this column here. This column runs between two nodes. It runs between this node and this node. Okay? Now, how this column deforms is based on the stiffness of the bottom node and the top node, right? Because where is this column going to move? This column is only going to move wherever the top and the bottom points move, right? So I need to know what is the stiffness of this node, and I need to know what the stiffness of this node is. How to calculate the stiffness of this node? It's based on the stiffness of everything that's connected into it. So this beam, this beam, this beam, and this beam, right? If I know the stiffnesses of each of these, I can calculate the stiffness of this node. Okay? When I say the stiffness of the node, what I'm really talking about is a value called gamma. So gamma is a coefficient, it's like a value, a ratio of the stiffnesses of the beams connecting into it and the columns connecting into it. There's a formula, you'll get it when you see it in the lecture, but that's basically what it is. Right? So there's a gamma value for this top node, let's call it gamma top. There's a gamma value for the bottom node, let's call it gamma bottom. And using these two and the original length, I can then figure out what the effective length for the element is. Okay? And once I have the effective length of the element, I can just chuck it back into my normal buckling formula and get the capacity of the column. Make sense? Yeah? Make sense so far? So this is gamma method. Just an extension on compression. So the way you'll see it happen in the course is there'll be 1 week where he'll be just talking about compression alone. And then the next topic of that will be compression with the gamma method. The actual formula for compression stays the same. The only difference between the two is, first when it's being introduced to you, it'll just be just a column, right? Almost experimental, like we were talking about earlier. And then later when it's introduced with gamma method, that's when it starts to get interesting, because that's when we look at it in terms of frames, okay? Now, where this gets a lot more fun, I use fun loosely here, is you will also see questions where he'll start giving you things in 3D. Okay, so you'll have a picture of a frame in 3D. They'll show you what's happening on this side, they'll show you what's happening on this side, and then based on that, calculate the capacity of one column here in the middle. Okay? The beauty about the gamma method is you can extrapolate that to however many dimensions you want. Obviously, well, we only get with 3. But basically, it's the same idea. Calculate the stiffness of the node at the top, stiffness of the node at the bottom, and then you'll be able to calculate what the effective length is. Okay? The only thing, of course, that's interesting is when you're calculating the stiffness of the node at the top, we take into account the beams and the columns that are framing into that node from all directions. Okay? And in our case, it'll just be 3D. Okay, so now I want to go back to this thing that I had earlier. So that's compression design. So there's suction failure and there's buckling failure, and you can do the same using the gamma method. And then the gamma method basically hooks into buckling failure as an extra step if you've got a complicated structure. Any questions on compression? No? Okay. The next topic is flexural design. Now, flexural design is basically the design of beams. Okay? So, give you a simple example. If you have a simply supported beam like this, where you've got a pin support on the left hand side and a roller support on the right hand side, okay, and you have a point load, what does the bending moment diagram look like? Triangle? Okay. Where would you draw the triangle? On the top or on the bottom?
On the top.
Why? Yeah, correct. So if you apply a load here, you're right, it'll sag. But I'm talking about the bending moment diagram, right? Is it a positive? Okay, let's look at the signs, right? Is this a positive moment? Does this cause a positive moment on the beam, or a negative moment? Yeah. Positive moment, correct. Okay. The reason why I bring this up is because what you've done in Eng 1300 so far, it might have been taught to you where the bending moment diagrams are just drawn as graphs where right side is up. Okay. If you've done structural analysis with EHAB, 2303 with EHAB, then you already know what I'm about to say, but the bending moment diagram must always be drawn on the tension side. Always. Okay? That's really, really important because nowhere in structural engineering will you ever see a bending moment drawn the other way around. Okay? So in this case, the bending moment diagram is drawn like this. And, oh, it's horrible. Okay? That's the bending moment diagram. I put the plus here. Okay? But in reality, just to give you a heads up, like when you do work as a structural engineer, if that's what you pursue, if you're looking at bending moment diagrams, even signs don't matter. Like no one cares if it's like a positive or a negative moment. Like the sign doesn't matter. Literally, it's the shape. That's it. Okay, and which side it's drawn on matters a lot. So why do I say drawn on the tension side? Because when this entire thing sags, so you think about it, a big piece of steel like this, when it sags, the bottom stretches out and the top compresses in, right? When it sags. So because on the bottom, the fibers are pulling apart, the bottom fiber is in tension, the top fiber is in compression. So the moment is drawn on the tension side. So therefore this whole thing is drawn on the bottom. That's really, really important, okay? So basically, when we're looking at steel design, right? For bending, we ask ourselves again, we start with the failure modes. How's it going to fail? Okay. So for steel design, I'm just going to check right here. Right? Okay. For steel design, when it comes to bending, really what we're looking at is buckling. Okay? Now, this is where everyone gets confused, and I just want to make it clear. There's two types of buckling. One buckling is because of because of compression, right? And that's just called buckling. The buckling that happens because of bending, which is this, okay? That is called lateral torsional buckling. Okay, I just want to make it clear here. So this is called lateral torsional buckling. Okay? Why do we say lateral torsional buckling? And how is that different from the column buckling we did before? Column buckling is really simple, right? You've got an I section or whatever steel cross section coming up, you push it down and it creates this S shape, whatever, right? That's just normal buckling. Lateral torsional buckling is something that happens because of bending. Okay? Now, I just want to make it clear. Whenever people say bending in this course, they're talking about what happens to an element because you have a load that is perpendicular to its longitudinal axis. Okay? So for example, in this case, you've got a beam. If you put a load like this, that'll cause bending. Okay? So bending is something that has moments involved. It's something like this. Only beams go through bending. Okay? I'll just make that clear. Now, a column can go through bending as well, but that is if it's only hit with a sideways load, right? If you've got a load that's coming up on top for a column and it buckles, would we call that bending? We won't. We'll call that buckling, right? Two different phenomena. Now, what happens when you take a beam and you bend it like this? Okay? I'll explain why this is called lateral torsional buckling. So, I want to imagine now that this is an I section. Okay, this is pizzas is so distracting. So this is an I section. Okay, imagine this is sticking out of the board. Okay, so this is sticking straight out of the board, and I apply a load on the top. Okay. This entire beam here sticking out of the board is going to bend, right? Okay. Now, what happens when I bend it? Like if I apply enough load on it, how is it going to buckle? This is the question, right? The buckling that's going to happen will cause two things. The first thing, what you'll realize is this cross section will actually start to move. Okay, so imagine this sticking out of the board. If I apply a strong enough load on it, what will happen is in the middle of the beam, right? Let's say there's a pin support on that end, there's a pin support on this end, right? If I apply a strong enough load on it, what will happen is this cross section will move, translate horizontally. Okay, and the next thing it will do is it will twist. So maybe I'll show you this way is better. Oh yeah. So imagine that is sticking out of the board, right? You will get something that ends up looking like that. I think one of the years I taught this actually had a roll with but yeah, if you get the idea that I'm talking about, it shifts, right, and it twists.
It's a bit too. But yeah.
See about it. Probably won't do this, but you get the idea. So there's two things that are happening, right? One is it shifts, and the other is it twists. Both of those happen. And that's when it gets really, really weak and then it fails. That's a very specific type of buckling that's called lateral torsional buckling, which is half the screen here. And that will only happen if there's a bending load that's applied. So everything that's covered in the bending chapter is figuring out how much moment has to be applied onto the element before that happens. Okay? Now think about it. How can I stop this from happening? Right? How can I stop this thing from bending like that? What if in the plane of the beam, right? So let's say this is the beam. What if I had extra beams that were framing into the top like that? Because in real life, you'll have beams that are crisscrossing, right, when you're holding up a floor. So in this case, let's say I had a beam that was framing in like that. Do you think this beam here that's coming in, so imagine this sticking on the board again, I have beams that are framing in, right, at particular discrete spacings. Do you think this would stop it from twisting? It would, right? So if I have more restraints, these are lateral restraints. If I had more lateral restraints, then the capacity of the beam increases, right? So everything you will cover in the bending chapter and the flexural chapter is basically looking at that, right? There are 3 types of restraints you can have, right? And already 2 types of restraints. The third one is unrestrained. That's not restraint. That's the lack of restraint. But looking at the different types of restraints and figuring out how does that change the formula to calculate the moment. Okay, but what I want you to remember is when you're learning that subject, when you're learning that topic, what's really, really important is figuring out physically what's happening to the beam. Because if you understand that, then the formulas will make sense. Okay? So that's the flexural chapter in a nutshell. Now, so here we're looking at basically preventing lateral torsional buckling. Okay? Now, the fourth part of this course is connection design. Oh, sorry, before I move on, under flexural design, the other thing that you'll learn is serviceability. Okay? What serviceability covers is how much will this thing deflect. Okay, so for example, if you've got a floor and there's a beam that's running under it, if I step on this floor, maybe the beam is strong enough to hold me up, right? But it could deflect a lot, right? So my job here is to figure out not only what happens in the ultimate case, but what happens in an everyday situation, right? In an everyday situation with the people walking on it all the time, yeah, it might not break, but it might deflect, right? Like an elastic deflection, and we need to prevent that, okay? So there is a topic within flexural design that teaches you how to calculate the deflection of a beam due to the loads and the restraints or whatever that are applied. And of course, you've got to check that against a sagging limit, right? So in most structures, you'll have a sag limit, which is length divided by 250 or length divided by 500, whatever it is. And basically that is like the code requirement for the maximum sag you can have for a beam. And that comes under the flexural design chapter. Okay, serviceability really, really important. Connection design, which is the second last part of the course, basically touches on 2 types of connections in particular. Okay, you've seen a small snippet of this from what Will had gone through for week 1/2. That is your bolted connection. Okay, and the second part of that is welded connections. These are the 2 connection types you'll see in the course. Essentially, the way the questions will show up, I think we'll show a little bit of that as well, is you might be given a connection detail, and then the question will basically ask you what's the capacity of this connection. Okay, connections are really important because imagine you've got a part of a building that connects a beam to a column, right? If you calculate the strength of the column and you're like, okay, so the column, I know how strong the column is, it'll be fine. And you calculate how strong the beam is and you're like, yeah, the beam is going to be fine, this building is going to survive, it's awesome, let's go get drinks, right? If that's the situation, but you did not design your connection properly, then the weak point of the building could be your connection, right? So you have to design your connection to take the loads that you're intending. So for example, if you intend for this column to experience 50 kilonewtons, let's say this column is going to experience 80 kilonewtons, this connection needs to take that amount of force going zipping through it, right? If you've got one beam here and another beam here, and this beam was supposed to transfer all of the bending and rotation into this beam, then you better make sure the connection in the middle can take it. Right, so that's why connection design is really important. So this chapter on connection design covers two types of connections, and formulas are also pretty basic, which are in the notes and in the lectures. Bolted connections, and then the other thing is welded connections. Okay, and it'll go through different types of welds. The formula changes a little bit. You know, if you're using a 41 MPa weld or a 48 MPa weld, it changes depending on what type of electrode you're using, what type of welding is used on site, etc. Basically, chuck in a different number into the formula, you get the answer. Okay, that's connection design. The last part, which strings all of this together, is called beam column design. Now, how is this different from beams or columns? Well, basically, what a beam column is a column. Fundamentally, it's a column that goes through bending, like a beam. Where will you see this? You'll see this in buildings. So for example, if I have, again, a frame that I draw here like that, you have vertical loads, right? So hence columns going through compression, but you also have wind, right? So what is the wind causing? If you forget about the gravity loads here, you've got columns here. The wind that's coming on this side is going to cause the column to bend, right? Flexural bending. So flexural just means bending. Yeah, so you get the idea? So this makes it behave like a beam. This gives it beam behavior. These loads on the top give it column behavior, right? So these things here, these vertical elements become beam columns, because they're going through two things at the same time, right? You're giving them, you're putting them in compression, but you're also forcing them to bend, right? So the question now becomes, how do you design that? Okay, and what you'll find is designing a beam column is just a summation of everything you've learned before that chapter, right? So you've learned how to design a beams. Imagine this is a beam and check it for this load, okay? You know how to design columns. Imagine this is a column and check it for this load for compression. Then you've got to see, all right, so it works for bending, it works for compression. Will it work if they both happen at the same time? Then there's another formula that checks combined behavior when it happens at the same time. Okay, and there's a few other things, and then probably to check this for compression, you'll probably end up using gamma method as well. Right, so ultimately, this last chapter here, it's good that they put it all the way at the end, and that's because you basically only learn one or two new steps. The rest of a beam column question basically very nicely pulls together everything that you've done before, all the way till the start. Okay, so that's basically what beam column design is, and in a nutshell, that's the entire course. That's steel structures. Okay. So when it comes to exam time and that sort of thing, whenever I demonstrate the subject, I always say the most efficient way to revise for this course is do these questions, right? Because if you can do these questions, you're pretty much like 90% there already, right? Because to answer a beam column question, you need to know compression design, you need to know flexural design, gamma method, which is like a big chunk of like the middle 2/3 of the course, right? But yeah, that's basically in a nutshell. Right? The main things to know is what I've just gone through with you is like maybe 3/4 of the course conceptually. There's still a quarter that we've left out just because for lifetime. But the most important thing in this course is understanding the concept behind it. Right? And albeit it's also the hardest part of the course because you'll be asked to look at things from a 3D point of view, etc., even though everything's printed on a piece of paper. So as much as you can, try and visualize what's happening in 3D, and try and visualize the failure modes, like visualize the thing failing, right? And intuitively you'll be able to understand which formula to use when. Okay, but if you understand it, this course is really not that hard because the questions all sort of look the same, right? There's only a certain number of ways you can ask someone. You can ask someone how to design a beam or ask someone to design a column. Right? Beams and columns generally look the same, right? Yeah, so if you do enough of those questions and you practice, what you'll find is the formulas, if you know what step 1 to step 8 is, or whatever it is, right, that always stays the same. If you do enough questions enough times, you'll end up memorizing it almost. Okay, but the important thing to get there, it might be a bit daunting at the start. The important thing is to get over that initial learning curve and try and understand what's happening, and then you'll be sweet. Okay. So hopefully what we've been able to cover during this crash course is maybe week 1 or a little bit of week 2 in detail, which is what Will had covered before with the formulas. And the rest of this, hopefully you get just a conceptual understanding of the key parts of the course. And then hopefully when you start going to the lectures, you can fill in the blanks. Cool. Any questions? No? All right.
Round of applause for Prash. Wow, it's the best crash course I've ever seen in my life. All right.